Okay, now question 3, part A. Potassium and potassium chloride forms lattice structure in solid state. Is asking reason, predict with reason the electrical conductivity of potassium solid and KCl solid. Now we know that potassium solid is a metal and KCl solid is a ionic compound. Potassium is a metal whereas KCl is an ionic compound. It's an ionic compound. For metals are good conductor of currents in solid state due to the presence of good conductors of current in solid state due to the presence of delocalized valence electrons. Because the delocalized valence electron, delocalized C of mobile electron or valence electron, C of valence electrons. These delocalized C of valence electrons, they act as carriers of current and they act as carriers of current. Thus they conduct current. Hence, potassium is a good conductor in solid state. K is a good conductor in solid state. Whereas, in case of KCl, which is an ionic compound, is a bad conductor of current in solid state. Why? Because here the ions are the carriers of current and they are not free to move. Ions are not free to move. Not free to move. Ions which are carriers of current. Ions are the carriers of current and they are not free to move. Therefore, it cannot conduct current in solid state. Thus, KCl is a bad conductor, whereas potassium metal is a good conductor of current. B part for question 3. Two electrolytic cells are connected in series with each other. All electrodes are inert. These are two electrolytic cells, one containing copper sulfate, another containing dilute KCl. State the half equation for the reaction occurring at each electrode in cell 2 using section 24 of the data booklet. Okay. Section 24 of the data booklet, we know that it is dilute KCl, and dilute KCl has what? It has OH minus ions and H plus ions. Along with K plus and Cl minus ion, it has OH minus ion and H plus ions. And at anode is an electrolytic cell. At anode is positive. Anode is positive electrode. Here already written positive electrode. The OH ions of this KCl, aqueous KCl, they will move towards anode and they will undergo oxidation to form oxygen and water plus electrons are given out. If I balance it, there will be 4 and then 4 OH minus and then 2 H2O. This will be the balanced equation at anode. Whereas at cathode, the H plus ions, they will move towards cathode. Instead of K plus, H plus will have more tendency to lose charge. They will go to cathode, negative electrode, accept the 2 electrons and convert into hydrogen gas. This is given out. These are aqueous. Here oxygen gas is produced and there hydrogen gas is produced. So this is the equation taking place at the 2 electrodes. Instead of K plus and Cl minus ions, H plus and OH ion will go because they have more tendency to lose their charge. The second subpart of question 3, part B. Identify the product at the anode in cell 1. At cell 1, the product at anode. Cell 1 contains copper sulfate, which contains Cu2 plus, H plus and SO4 2 minus and OH minus ions. In case of Cu2 plus and H plus, the Cu2 plus has more tendency to lose charge. Therefore, they will go to negative electrode and they will form Cu. Whereas OH minus will have a tendency to lose charge. In case of this, OH minus will go to the positive electrode and they will convert into oxygen gas. Oxygen gas is produced at the positive electrode and Cu is produced at the oxygen gas is produced at the positive electrode, which is anode, and copper is produced at the negative electrode, which is cathode. So the answer, which is asking identify the product at anode in cell 1. Product at anode in cell 1 will be oxygen gas. Next, determine the mole ratio of non-ionic products formed at cathode in cell 1 and cell 2. Non-ionic products formed at cathode in cell 1 and cell 2. The non-ionic products formed at cell 1, here the non-ionic product will be hydrogen and here it is copper. Non-ionic products formed at cathode in cell 1 and cell 2. In cell 1, copper is produced, and in cell 2, hydrogen gas is produced. Since Cu 2 plus is converting into Cu, it requires 2 moles of electron, and similarly H plus is converting into twice of H plus converting into H2, and it also requires 2 moles of electron. Thus the molar ratio formed is 1:1. The molar ratio of the ionic product formed at the two electrode, because they require same number of electrons, therefore with equal quantity of charge they will produce same moles, that is 1:1. 1 mole of copper requires 2 moles of electron. Similarly, 1 mole of hydrogen gas also requires 2 mole of electron. The ratio is 1:1. State the number of each type of subatomic particles in the potassium 41, 19 and plus charge, that is, it has lost 1 electron. Protons are 19 because atomic number is 19. Electrons are 18 because it has lost 1 electron, and neutrons are 41 minus 19. That is equals to 22. So these are the number of electron, proton and neutron in potassium ion K plus ion. This is part C. Question 3. Part B 1 and 2 and 3 are done, and part C. Part D says, outline the evidence that electrons in potassium atoms occupies 4 main energy levels. Now the evidence we have to give that potassium, the electrons occupies the 4 main energy levels. The first evidence is potassium is present in the fourth shell. Potassium is present in, that is, the last electron enters the fourth shell. That is, potassium is present in the fourth period of the periodic table, fourth period, and the number of period tells about the last shell produced. That is present in the fourth period of the periodic table. That has 4 main shells, filled. And that has 4 main shells filled, which are K, L, M, N. The last electron enters in the N subshell, and the configuration of potassium is K equals to 19, 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. The last electron enters in S subshell of the fourth shell, S subshell of fourth energy level. As we can say, potassium atom occupies 4 main energy levels. Or along with it, we can also say the principal quantum number, which is N for potassium, is 4. Why? Because the last electron is 4s1, last electron, N is 4. So these are the evidences which shows potassium occupies 4 main energy levels. The first evidence is potassium is found in the fourth period of the periodic table. 4 main energy shells are filled, KLMN. Configuration is 3p6 4s1. Last electron enters in the S subshell of fourth energy cell, and thus we can say the principal quantum number of potassium is 4. Okay, so this is the answer for part D. Now the part E, potassium reacts with water to produce potassium hydroxide, and reaction is 2K plus 2H2 give you twice of KOH plus hydrogen. Calculate the enthalpy of reaction in kilojoules per mole when 1 mole of potassium reacts with water. 1 mole of potassium reacts with water. Use section 12 of the data booklet. Delta H of KOH is 481.8. Enthalpy of formation of KOH is 481.8. I have to calculate enthalpy of reaction. Delta RH degree of reaction equals to, when we add enthalpy of formations, then the formula for enthalpy of reaction is delta RH equals to summation delta HF degree of products, enthalpy of formation of products, minus summation delta FH degree of summation delta FH degree, delta FH degree, that is enthalpy of formation of products, minus summation delta FH degree, enthalpy of formation of reactants. This is the formula. And from data booklet section 12, we know that enthalpy of formation of water, delta FH degree for H2O is given, which is equals to minus 286 kilojoule per mole. It is given to us. And delta Fs degree for element in the elemental states like hydrogen, that is equals to 0. And for potassium, which is also the elemental state of potassium K, delta Fs degree is also equal to 0. For potassium and hydrogen, delta Fs degree is 0. Putting the values in this equation, delta RH degree is equals to delta RH degree equals to summation enthalpy of formation of product twice of KOH. 2 KOH is minus 481.8 minus 481.8 2 into minus 481.8 plus 0, which is the enthalpy of hydrogen. This is enthalpy of products, enthalpy of formation of products, minus 2 into 0 plus 2H2O. 2H2O, the enthalpy of formation of water is minus 286 into minus 286 into 2. Enthalpy of reaction, that is delta RH degree, will be equals to 2 into minus 481.8 is minus 963.2 minus 286 into 2 is 572. That comes out to be delta RH degree equals to minus 391.2 divided by 2, because I want in kilojoule per mole, divided by 2 equals to 195.6 minus 195.6 kilojoule per mole will be the answer. Okay, this will be the answer for this question. Minus 195.6 kilojoule per mole. Next question is, describe the difference between the reactions of sodium and potassium with water. When sodium and potassium reacts with water, both form their respective hydroxide NaOH and KOH. But the reaction in sodium takes place vigorously, whereas in potassium it takes place explosively, because potassium is it takes place violently. Explosively in or violently, I can write, it takes place violently. So in potassium, the reaction is taking place violently. Rapid release of hydrogen gas with rapid release of hydrogen gas. Release of hydrogen. यहाँ पे होगा rapid release, here it will be rapid release of hydrogen. So this will be the difference between the reaction of sodium and potassium with water. Next is demonstrate with an equation the acid-base nature of K2O. We know that K2O is basic in nature. The oxides of potassium, they are basic. So when I react K2O solid with H2SO4 or HCl, H2SO4, which is an acid, here it will act as base. This will be an acid. What it will form? It will form K2SO4, which is a salt plus water. K2SO4 will be aqueous and water. If I balance it, the equation is 2H2O, yes, 2 hydrogen, and SO4, 1 oxygen balance. This is a balanced equation. Next is question 4, which says sulfur trioxide is an important compound in industry and has more than one possible Lewis structure, electron dot structure. Sketch the two Lewis structures for SO2, one of which obeys the octet rule and one which does not. First, I will draw the structure which obeys octet rule. That is, in this, the sulfur will have double bond O, single bond O, and a coordinate bond O. 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4 electrons here. And 1, 2, 3, 4, 5, 6 here. Sulfur is octet complete. Therefore, this is as per the octet rule. When we talk about octet axis compound of sulfur, so instead of a coordinate bond, there can be a double bond, then here a double bond, and also a double bond. Oxygen is 6 electron, out of which 2 has been shared by sulfur. This oxygen also has 6 electron, 2 shared by sulfur, and this oxygen also has 6 electron, 2 shared by sulfur. 2, 2, 2, 4 and 2, 6, 6 of sulfur shared by 6 of oxygen. It has 12 electrons, therefore it is an octet axis compound. 4, 4, 8 and 4, 12. Hence it is an octet axis compound. It has 8 electrons, therefore it is an octet sufficient compound. Okay, so these are the two structures of SO2. Question number 4a, part 1. Next is state how chemists decide which Lewis structures electron dot structure more stable. The stability of electron dot structure decided by finding the biformal charge. By help of formal charge, the structure which have all atoms formal charge equal to 0. Formal charge is equal to 0, that will be more stable. That is more stable. The chemist can find out formal charge, and with the help of formal charge we can decide which structure is more stable. Part 3, and part 3 says predict the length of each sulfur oxygen bond in picometers using section 10 of the data booklet. Since in SO3 delocalization of the pi electron cloud will take place, delocalization of pi electron cloud, that is, it will show resonance. Resonance will be there. Thus, all three bonds, all three SO bonds will have partial double bond characteristic. Partial double bond characteristic. Bond order is 1 by 3. Hence, the bond length of SO bonds will be between S single bond O and S double bond O. That is between 161 picometers to 143 picometers. This will be the bond length of SO bond in SO3. Next question is, suggest why atmospheric SO3 is an environmental concern. Since SO3 is an acidic gas, it is an important pollutant. It's a pollutant. It is an atmospheric or air pollutant, and it combines with rainwater to form, it dissolves with rainwater to form sulfuric acid, which can cause acid rain, and that can result in acid rain. Therefore, it is an environmental concern. State the name of post-combustion method used to lower the quantity of SO3 released in the atmosphere. After combustion of the coal, the flue gas are produced, so we can use flue gas desulfurization process. Flue gas desulfurization process can be done, in which the flue gas could be passed through the solutions of calcium oxide so that they can react with SO3 to form calcium sulfate, CaSO4. Large tanks contain slurry of calcium oxide. When we pass sulfur trioxide gas containing flue gas, sulfur trioxide pollutant containing flue gas, it forms calcium sulfate. Sulfur trioxide will react with CaO and convert into calcium sulfate, thus could be removed. This is called as flue gas desulfurization process. This is one of the methods by which we can remove sulfur trioxide from air. Next is part D, which says SO3 is made by using contact process. SO2 on reacting with oxygen form SO3. The delta H of the reaction is less than 0, that is an exothermic reaction. This tells it is exothermic. Sketch a potential energy profile for this reaction on the axis provided and label EA, including labels on the axis. We have to label EA and axis. When I want to make a potential energy profile, the y-axis contains potential energy. The y-axis is potential energy, or the energy axis, whereas the x-axis is the reaction coordinates. Reaction coordinate or speed of the reaction. When we talk about an exothermic reaction, exothermic reactions are those in which the energy of reactants is greater than energy of product. So suppose this is the energy of reactant, this much energy is supplied to the reactant so that they got the energy barrier and converts into product. If I have to mark the various energies, this is my energy of reactant. From here to here it is ER, energy of reactant. This is energy of product, EP. From energy of reactant till the top, which is energy barrier, this is my activation energy, EA. And this is delta H, which is negative enthalpy of reaction. Okay, so this will be the graph EA from enthalpy of reactant. These are reactants and this is product. Exothermic reaction, the energy of product is less than energy of reactant. Delta H is the difference between reactant and product. This is energy of reactant, this is energy of product, and then activation energy. Next is explain why increasing temperature increases the rate of reaction. When we increase temperature, when temperature of a reaction is increased, the kinetic energy of the gas particle will increase. Thus, more number of reactants, kinetic energy of the reactant will increase. More of the reactants will have energy greater than activation energy. Now, more number of reactant particle will have energy greater than activation energy. Hence, more chances of successful collision. Chances of successful collisions. More chance of successful collisions, and frequency of collision will increase. Frequency of collision will increase. More chance of successful collision along with increase in frequency of collisions. Thus, rate of reaction will increase. Of reaction increases. Okay, so when you increase temperature, the kinetic energy of the reactant particle will increase. Thus, frequency of collision will increase, and there will be more number of particles having energy greater than activation energy. Thus, there's more chance of successful collisions, thereby increasing the rate of reaction. Now, next is vanadium pentoxide act as a catalyst. Explain how a catalyst increases the rate of reaction. Now, catalyst, which is a positive catalyst, takes a reaction to an alternate path. Having lower activation energy, lower EA or activation energy. Thus, more particles or the reactant particles will have energy greater than activation energy, and hence, since activation energy has been decreased, the more particle will have energy greater than activation, hence rate will increase, rate of reaction will increase. So what should be the answer? The catalyst takes the reaction to an alternate path which has lower activation energy, thus increases the rate of reaction, since more particle will have energy greater than activation energy. Next is during a reaction. Next question 4, part 4. During a reaction, V2O5 changes to V2O4. Identify the oxidation states of vanadium in each compound. For vanadium, let me take X to 2X plus. For oxide, it is -2 into 5, and it is a neutral compound equal to 0. X comes out to be +5. For V2O4, it is 2X plus -2 into 4, that is equal to 0. X comes out to be +4. Next question is state the equilibrium constant expression Kc for the production of 1 mole of SO3. The reaction is given SO2 plus half O2 give you SO3. The Kc is always equals to the concentration of product, which is SO3, upon the concentration of reactant, which is SO2, into O2 to the power 1 by 2. This will be the expression for Kc. Concentration of reactants, concentration of products upon concentration of reactant, SO3 upon SO2 into half of O2. Next question, part 6 is calculate the entropy change delta S degree in joule per Kelvin per mole for the production of 1 mole of SO3, and the absolute entropy values are given here. The reaction is SO2 plus half O2 gives you SO3. This was the reaction. Delta RS of reaction, that is standard entropy change of reaction, equals to summation standard entropy of delta RS, delta standard entropy of products, delta S of products, standard entropy of products minus summation standard entropy of the reactants. Delta Rs degree, that is equals to standard entropy of reaction, equals to product here is SO3 and that entropy is 256. 1 into 256.8. This is entropy of products minus entropy of reactants. Reactants is SO2. 1 into 248.2 plus half into 205.2, which is for oxygen. Half mole of oxygen is required. That will be the entropy of reactants. Thus delta Rs degree, standard entropy of reaction, comes out to be 256.8 minus 205. It comes out to be 256.8 minus 248.2 plus 102.6, and delta Rs standard entropy of reaction is 256.8 minus, the sum of these two is minus 350.8. That comes out to be delta Rs standard entropy of reaction equals to minus, it comes out to be, when I calculate it, it comes out to be minus 94 joule per Kelvin per mole. This will be the answer for entropy change for the reaction. SO2 plus O2 gives you SO3. Okay, entropy of products minus entropy of reactants, and we get minus 94 joule per Kelvin per mole. Next, part 7 is outlined with reference to the equation why the sign for the entropy change obtained in part 4 is expected. We obtained a negative sign in the part 6. The negative entropy delta Rs is coming out to be negative. The reason for this is the number of moles of gaseous products in this reaction, which is SO3, is less than, which is equal to 1, is less than the number of moles of gaseous reactant, which is equal to SO2 plus half O2, that is 1.5. reactants, that is 1 plus 0.5, that is equals to 1.5. Since the moles of reactants is greater than moles of product, hence entropy should be negative as expected, as we calculated. Entropy is negative because gaseous moles of products is less than gaseous moles of reactant. Okay, this should be the answer. Next, 8th part is calculate the value of Gibbs free energy delta G degree for the reaction in kilojule per mole at 773 Kelvin, section 1 of the data booklet, and delta H is minus 98.5. If you did not obtain the answer, it is 100 joule, but we had obtained the answer, which is 94. Now the formula, delta G equals to delta H minus T delta S. This is the formula for calculating Gibbs free energy, and delta G will be equals to delta H given is minus 98.5. Minus 98.5 minus temperature is 773. 773 into delta S was minus 94 divided by 1000. Why? Because it is in kilojoule, this is in joule, so we'll divide it by 1000. It comes out to be delta G equals to minus 98.5 minus 72.66 minus 72.66. It will be a minus sign inside also, minus 72.6, minus 98.5 minus 72.66. Okay, when we solve it, delta G equals to minus 98.5 plus 72.66. That comes out to be delta G equals to minus 25.84 kilojoule per mole. This will be the answer. Question is, calculate the value of equilibrium constant Kc for the formation of SO3 at 773 Kelvin using section 1 and 2 of the data booklet. And if you did not obtain the answer, take 25. We got the answer and we will use that only. We have to find out the equilibrium constant Kc by using delta G. Gives energy, and the relationship between, we know that delta G equals to minus RT ln Kc, and we calculated the value of delta G, which is negative. I can say minus delta G equals to minus RT ln Kc. This minus sign can be gone. I can say delta G equals to RT ln Kc, and I will use this formula to find for the formula delta G equals to RT ln Kc, and we have to find out Kc. Therefore, delta G, which we had calculated, was 25.838. At 25 point, we find it out. Delta G was 25.84. 25.84 equals to R 8.314 divided by 1000, because R is in joules and delta G in kilojoule. Pause करके. Delta G is 25.880, R is 8.314 divided by 1000 into temperature is 773 Kelvin, and ln Kc I require. Okay, thus I can say ln Kc equals to 25.84 upon 8.314 into 773 and multiply by 1000. That comes out to be, ln Kc comes out to be 4.02. If I calculate, ln Kc comes out to be 4.02, and Kc equals to e to the power 4.02. If you want to calculate Kc, then Kc will be equals to, by using the calculators I find it out, Kc equals to 55.70. This is the value of Kc. Thus 55.70 is the answer. Nth part of this question is, a flask contains 0.120 mole per dm cube of SO2, 0.050 mole per dm cube of O2, and 0.150 mole per dm cube of SO3 at 773 Kelvin. Deduce whether the system is at equilibrium, in which direction the reaction will proceed spontaneously if not in equilibrium. For such question, we have to find out QC. Now, QC for the equation, now we can find out QC in two ways. Either you can find out equation QC in terms of 2 moles of SO3 or 1 mole of SO3. I am doing it by the help of 2 moles of SO3, and then I will find it out, then I will underroot it. For my formula, QC equals to SO3 square, because the equation I am using is 2SO2 plus O2 gives you twice of SO3. This can be the equation, which was the first equation in the question. After that, they had done it for 1 mole. So we can use 1 mole, or we can use this equation, and then we can underroot the Kc to find out for 1 mole. This will be my equation. 2SO2 plus O2 give you twice of SO3. As per this equation, QC will be equals to SO2 square, SO3 square upon SO2 square into O2. Putting the values of SO3 and SO2 and O2, I get 0.150 whole square upon 0.120 whole square into 0.050, which is the concentrations of sulfur dioxide and oxygen. On calculation, I find QC is coming out to be 31.25, which is for 2 mole. QC for half will be under root of this, under root of QC, and that will be root of 31.25, that is equals to 5.6 for 1 mole. If I am taking it for 1 mole, this for 2 moles of SO3. For 1 mole, we can do from both. Either you compare with 2 moles or you can compare with 1 mole. We can do both, because in both cases, my QC is less than Kc. QC is less than Kc, because Kc is 55.70 and QC is coming 31.25 or 5.6. Both you can do. Now, since QC is less than Kc, therefore, in order to reach equilibrium, the reaction should move. The reaction should increase the concentration of product, direction should move towards right hand side, towards product side or right hand side. We can write right hand or product side or product side, so that the concentration of product could increase and it can become equal to Kc. That's all about this question.